Hey guys, welcome back. So let's look at the first question. Show that the function f from r star to r star defined by f of x equals 1 by x is 1 to 1 and onto, where r star is the set of all non-zero real numbers. Is the result true if the domain r star is replaced by n, with codomain being the same as r star? Right. So before you solve this question, you need to be clear about the terms of what a set is, what a codomain is, what a codomain is, and I'm assuming you're pretty familiar with almost all of those things. Basically, every function has a domain and a codomain, right? Any function you have will have a set codomain and a codomain. Let's say you have a function mapped from domain x to codomain y, and in that function, every set, this is a set with multiple elements called the domain. This is a set with multiple elements called the codomain, and you will have a function mapped in some way like that. So a function is said to be one to one if every element in every distinct element in x is mapped to only one distinct element in y, the codomain. So if a function is one to one, every element in the domain will be mapped to one element in the codomain. There won't be anything left out. So every single one will have at least one mapping. It's possible that you may have extra here. It's possible that there may not be some of these elements missing out, not being mapped to anything here, but everything here will be mapped to something over here. And if it is onto, then every element here will also be mapped to some element over here. If it is onto one and onto, then every single one of these elements will be mapped to every single one of these elements. So basically, that's what we have to prove in this case. So the second thing you need to know is what is this r star, right? So in this question, they've given us that there's a function f which is mapped from r star to r star. And they've told us that r star is the set of all non-zero real numbers. So basically r star is basically set of real numbers minus 0. You just remove 0 out of the set of all real numbers, right? Why was this done? Because the function given is, look at the function given, if it's 1 by x, right? So if you had 0 as part of this domain, then you would have an undefined function. The function would not be defined at that particular point. So to eliminate that possibility, they defined the domain and the codomain in such a way that we don't have 0 as one of the elements, right? So to prove one to one, what do we do? So first, let's try to prove whether the function is one to one. Now, if the function is one to one, what would happen? If you know that there are two equal elements, let's say you have these two elements, right? So let's say you have these two sets, r star and r star, for this function f, right? This is function f of x is 1 by x. So if there are two different elements in the codomain which are equal, then if you can prove that if there are two equal elements here, and if you can prove that if you try to figure out what is the corresponding element in the domain, and if you can prove that they are also equal, then you know that if you have to have equal elements, if you need to have two different elements here, and if they are equal, then it's definitely true that they are coming from the same element. You cannot have different elements giving you the same possibility in the codomain. I hope you understood that. Basically, the idea is, if you have an element here which is equal to some other element here, it's possible in some functions, you could have a function like this. So if you have one element here and another element here, let's say these two are equal, it's possible that this comes from a different element in this, and this comes from a different element in this. Both these elements could point to the same value. So basically, it would look like this. It would look like this. This is pointing to this is pointing to the same thing. These two are equal, right? Basically, they are the same element. So also remember that in sets, you cannot write the same element twice. You need to have it only once, right? So if this is the case, this is how the function would look. But you want the function to look like this. This is basically the reverse, but you want a function to look like this. Only one function, only one element here is mapped to one element here. One element is mapped to only one element here. Is that true or not? We need to figure that out. Right. So if we assume that f of x1 equals f of x2, what is f of x1? F of x1 would be 1 by x, right? So the function is this. So if f of x1 would be 1 by x1, f of x2 would be 1 by x2. So what do we get from here? We get x1 equals x2. So what we have got from here, if we assume that we have two similar elements which are equal in the codomain, in the codomain, then we proved that they have to come from the same element. Right? It's possible in some case. If it's possible in some cases that you don't get this, it's possible that you end up getting x1 is not equal to x2 and still have these two elements being the same. But in this case, that's not true. So this is a one-to-one function. This means, so one-to-one function, when you have a one-to-one function, if you have an element which is equal in the codomain, then you'll always get it from only one single element. You won't have multiple elements giving you the same value. That is the meaning of one-to-one. If not, it will be many to one. Right. So let's see how we can prove it's onto. And by the way, this is also called a one-to-one function is also called an injective function, right? A one-to-one function is also called an injective function, and onto function is also called a surjective. Right. Now, what is onto? Onto is where you have every element in the codomain. R star is our codomain here. Every element in our codomain, every element should have at least one specific element mapped. It could be the same element, but it has to have at least one mapping. If it is distinct, then it's also one-to-one. So that's the idea, right? So every element in this codomain needs to have at least one element. You cannot have any free elements lying around. Right? So now, how do you prove it is onto? To prove onto, we need to prove that for every y in the codomain, there exists a 1 by x in the domain. Such that f of x is y, which would give you f of x is y. That's what I was telling you, right? So you need to prove that every single element in this codomain has at least one element in the domain. In this case, it happens to be 1 by x because that's how f of x is designed. That's how f of x is defined, right? Now, how do you prove that? So, what is our codomain? Our codomain is R star. Our codomain is R star, which is a set of all real numbers. So, for every y, can I not write a 1 by x? So for every, let's say you take a number 2, I can always get a 1 by 2 for that. Let's say you take a number, I don't know, like root 2. You can always write a 1 by root 2. So for every element, for a y in R star, you can always write a 1 by x, right? You can always figure out a 1 by x for that, such that y is equal to 1 by x. You can always figure out, right? So for example, if you want to find when y is 2, you can always find an x which is equal to equal to y, which is when divided by 1, you will get a 2. If you divide this by 1, you will get a 2, right? So you can always find an x such that this condition is true, because all of these values exist in R star as well. So since our domain is also R star has all of these values as well. And R star also has all values of y. So for every y, you can always find a 1 by x. So that means you can say that it is an onto function. So it is an onto function. For every y that belongs to R star, you can find an x such that 1 by x belongs to R star. Hence, f of x equals 1 by x is onto. That's how you would write it in an exam. Now let's go to the next part of the question. So the next part of the question is the result true if the domain R star is replaced by n with codomain being the same as R star? So this is the domain, this is the codomain, right? So they're asking if the result is true, will the result hold true if I replace my domain with n, the set of all natural numbers, and the codomain remains R star. will the result hold true? So if this is f of x equals 1 by x. So now the domain is only natural numbers, right? So the domain is only natural numbers. Will I be able to, for first, let's check for 1 to 1, right? So is it 1 to 1? And let's check for on to. The logic is basically the same. But if it has to be 1 to 1, as we discussed earlier, every element in n needs to be mapped to at least one element in R, right? Every element in n has to be mapped to at least one element in R, which will of course be true, right? So if it is f of x is 1 by x, for every x1, you can always find a 1 by x1 in R star. So that will be true. So if f of x1 is equal to f of x2, which means 1 by x1 is equal to 1 by x2. F of x1, let's say if x1 is 1 and x2 is also 1, then the result would also be 1 out of 1 by 1. This will also be part of R star. So this will still be 1 to 1. Will you be able to find for every y belongs to R star such that 1 by x belongs to n? Will you be able to find that? You will not be, because let's say if y is 3, right, which belongs to R star, obviously 1 by 3, you will end up with 1 by 3, which does not belong to n, right? So this is not an onto function. So every element in R star will not have, there will be a lot of elements left out in R star which will not have a mapping in here. But every element in here, you will still be able to find something over here, because this is a much bigger set. R star of real numbers is a huge set, much bigger than the set of natural numbers. So this is a one-to-one function, but not an onto function. Let's go to the next question. Okay, so this question is asking us to check the injectivity and the surjectivity of the following functions. So as we saw in the previous question, injectivity is just one-to-one, right? So injectivity just means one-to-one function, and surjectivity just means onto, right? So this injectivity makes sense, where you can see that if you have two sets, domain and the codomain, every element in domain will have only one element in the codomain. It's a one-to-one. You can see that it's injecting, right? So you're injecting this element to this element. So it's basically like, you can imagine like an injection happening over here from here. Only one to one, right? So it's like a needle piercing. That's an injectivity. You can think of it and remember it that way. And the other one is a surjectivity, where it's an onto function, where every element in the codomain will have at least one element in the domain. So you won't have any leftover elements over here, right? So that's the idea of injectivity and surjectivity. Now let's see which of these elements are passing these criteria. So the first one is f from natural number to natural numbers, where f of x is x square. So this domain is natural numbers and codomain is natural numbers, and the f of x is x square. So is it one-to-one? How do you find one-to-one? So one-to-one, you need to say that for f of x1 equals f of x2, you need to prove that x1 is x2. So for f of x1, you will get x1 square. F of x2, you get x2 square. So if x1 square equals x2 square, if you take the square root on both sides, you get x1 equals x2. So that condition works, right? So it is a one-to-one function. Now is it onto? So for every y that belongs to n, can you find an x? Can you find an x such that y equals x square? For every y, can you find? That is the question. So it means that for every single element that it is in y, you need to find an x such that y is equal to x square. And that's not going to happen, because y is a set of natural numbers and x is also a set of natural numbers. So let's say if y is 3, right? Can you find an x that belongs to n such that, this is a very important point. So for every y that belongs to n, can you find an x that belongs to n such that y equals x square? You can't, because let's say y is 3. So it will be x square is 3, right? So this means x would be equal to root 3, which does not belong to n, correct? So this makes it clear that this function is not an onto function. Every element in the codomain, every element in y will not have one mapping, will not have a mapping here. So 3 will not have a mapping, 5 will not have, only the perfect squares will have a mapping. So this makes the function not onto. So this is 1 to 1 but not onto. Right, so sorry. So this is also is injective but not surjective. This is injective but not surjective. Let's take the next one. So this question talks about, this is the second question, right? So in the second question talks about a function defined from the set of integers to integers and is the same function as the previous one. So we need to see whether it is injective or and surjective. Right. So to prove it's injective, what do we do? And by the way, n is a set of natural numbers. Z is the set of integers. So n is a set of natural numbers, right? So n is natural, Z is integers, Q is rational, R is real. So you need to know this or else you might make mistakes sometimes. Right. So if you want to prove it's injective, what do? We say f of x1, if f of x1 is f of x2, and we're able to prove that x1 is x2, then it is injective. So if f of x1 is f of x2, then f of x is x square, so f of x1 would be x1 square, f of x2 would be x2 square, which would mean x1 is x2. So that is true. So for every, this is injective. So for every element as an integer, you can always find another value which will be equal to its square. So for every integer you have, you'll always have a square. So in the domain of integers, it will always be an integer. Square of integer is always an integer. So that means, of course, it's true. Is it surjective? For every y that belongs to integers, can you find an x that belongs to integers such that y equals x square? Can you find an x for every y? So for example, x is the same one as last time, right? So we had the set of integers this time. If y is 3, then x would be root 3. And root 3 is not an integer. Does not belong to z. So this is not an onto function, because clearly every integer is not a perfect square, right? So it's the same idea as last time. Every natural number is not a perfect square. So that's the same idea. So this is not surjective. Let's go to the next question. Okay, let's look at the third question. So here we have a function going from, defined from the set R to the set R, so all real numbers, given by f of x is x square. Yeah, so this obviously is going to be both injective and surjective, right? So it's clear from our previous two examples. So is it injective or surjective? And surjective, maybe. So is it injective? Yes, because for every f of x1 equals f of x2, everything will always be equal. So x1 square is x2 square. So x1 equals x2. So it is injective. And usually when you have a smaller set, and if that's true, usually for the bigger set it's usually true, right? Because it contains all of the, not always, but usually you can think of it that way, but don't go by that. That's not a rule. Right? So it is injective. That's true. Is it surjective? So for every y that belongs to R, can you find an x that belongs to R such that y is equal to x square? Yes, right. So if a y is, let's say, -3, can you find a value of x which belongs to the real number which is equal to, and you square it, you can get -3? You can't. You can do it for imaginary numbers, but not for real numbers. So even this is not surjective. So it is not onto. Let's go to the next question. So here we have a function defined from the set of natural numbers to natural numbers, given by f of x is x cubed. So is this injective? Is this surjective? Right. So for f of x1, equals f of x2, which gives you x1 cube equals x2 cube. Does that mean x1 equals x2? Yeah, it does mean. So any number you cube it will always give you the same answer, right? So if you have two cubes, if you have 64 cube, if you have 64, if you cube that, you only get one answer, right? You're not going to get multiple answers. So that's always the case. Even for minus 64 is the same answer, by the way. Right, so this is injective. Is it surjective? For every y that belongs to n, can you find an x which belongs to n such that y equals x cube? For every y, can you find an x such that y equals x cube? No, you can't, obviously. No, not every natural number is a cube, right? So even you can take the same example 3, right? So you can take the same example 3, right? So if y equals 3, then x equals cube root of 3, because 3 is not a perfect cube, so it is not surjective. It's not, unfortunately, not surjective. So finding surjective functions are much more rare than finding injective functions. It's clearly true. And here we have the final one, f from set of integers given by f of x is x cube. And from our previous experience, it's obvious this is not going to be the case, right? So obviously every integer is not a perfect cube, so it's not going to be onto. It's not going to be surjective. It's very clear, right? So anyway, let's just go ahead and do our drill. Injective and surjective. We should never stop our drill. We can come to the answer very quickly. If it's a subjective exam like CBSE, you might still have to write the entire answer. But if it is an objective exam like the JEE Main, Advanced, or any other competitive exam, then you just mark your answer and just leave. You don't have to solve anything, right? That's the advantage in a competitive exam. So in this case, you know that f of x1 is f of x2. Then you know that x1 cube is x2 cube, which means x1 equals x2. That's always going to be the same. It's always going to be the case for all integers as well. An integer cube is always going to be an integer. So if you have two integers which are equal, and if you cube root them, you'll get only one integer. You're not going to get multiple integers. Now, is it surjective? So for every y that belongs to integers, can you find an x? Can you find an x such that x belongs to integers and y equals x cube? You obviously can't. If y equals 3, let's say y equals 5 for once, or minus 5, whatever you want to take. If y equals 5, you would get x equals cube root of 5, right? Cube root of 5, which is not, this does not belong to integers. So it is not an onto function or a surjective function. It's not surjective, but it is injective. Great. Let's move to the next question. Great. So in this question we need to prove that the greatest integer function, which is defined from the set of real numbers to the real numbers given by f of x is equal to the step of x, right? So this is the greatest integer function, is neither 1 to 1 nor onto, where step x, the box of x or step x, denotes the greatest integer less than or equal to x. Interesting question, right? So we need to talk about the greatest integer function. It's a very interesting function and very useful further down the line as well, right? When you solve questions in math and physics, it's going to be useful. So the greatest integer function is written as this, right? It's written by a box. It's called a box of x or a step of x, also called a box, usually called a step x or a box x, whatever you want to call it. It's also called GIF, not the GIF we use, but the greatest integer function. Other one is graphics interface format, just for your information anyway. So we need to prove that this function, which is going from a set of real numbers to real numbers, is 1 to 1, is neither 1 to 1 nor onto. And this is equal to the greatest integer less than or equal to x. So for example, the way this function works is, if you have x taken as 1.1, then this function would give you 1. it is equal to the greatest integer less than or equal to x. So if you have the step of 5, that would be 5. If you have a step of minus 8.3, that will be equal to the greatest integer less than or equal to x, which is, what is the integer less than minus 8.3? It is minus 9. It is not minus 8, because minus 8 is greater than 8.3. So this is how the greatest integer function works, right? So this puts you to a value which is less than or equal to the integer that is less than this value. So whatever value is inside this function, it will output a number which will be equal to the integer which is less than that or equal to that. That is the idea of the greatest integer function. Even though it says greatest integer, the idea is greatest integer less than or equal to x. It's not the integer which is greater than that value. So that's a little bit confusing, but you need to remember that. Right? Okay, so now we need to prove whether it's 1-to-1, neither 1-to-1 nor onto. Is it 1-to-1? So for 1-to-1, what do we need to prove? For f of x1 equals f of x2, we need to have x1 equals x2, right? So f of x1 would be step of x1. F of x2 would be step of x2. Now, does this imply if we have two values equal in a 1-to-1 in a greatest integer function, can we say x1 equals x2? No, because if you have the step of 1.2, this will also give you 1. If you have the step of 1.3, this will also give you 1. 1.1 also gives you 1. So x1 could be 1.2. x2 could be 1.3. Even though these are equal, these two are equal, right? See, 1 is equal to 1. But the x value may not be the same. This could be different values. And this is where you see it need not be a 1-to-1 function. So this does not imply x1 equals x2. So this is not a 1-to-1 function. It's not 1-to-1. That we have proved. So we need to prove it is not onto as well. How do we prove that? Onto. So for every y that belongs to R, can you find an x? Can you find an x that belongs to R such that y is equal to step of x? For every y, can you find? So let's say a y, for every y, can you find an x such that y is equal to step of x? Now, if let's say y is 2.3, can you find any value of x that can give you 2.3? No. For every y that belongs to R, you need to have some value of x which can give you that value. Only then you can say that this function is onto, right? So if y is 2.3, but the step function, which is the greatest integer function, can only give you values of integers. So it can never give you something like a 2.3 or a 3.8. You cannot get any decimal values or any other rational numbers, any of the irrational numbers. You cannot get any of those values. You can only get integers. If this was y belongs to z and x belongs to z, then yes, this would be an onto function. But in this case, it's not. You cannot find multiple values of y for which there exists a corresponding x value. So we have proved that it is neither 1-to-1 nor onto. Let's move to the next question. Awesome. So this question says, show that the modulus function f from R to R given by f of x is equal to mod x is neither 1-to-1 nor onto, where mod x is x if x is positive or 0 and mod x is minus x if x is negative. Great. So all of you have heard of the modulus function. So this is defined from the set of real numbers to real numbers, and we write it as f of x is equal to 2 dashes inside x, right? So the mod of x, where x would be, if x is greater than 0, greater than equal to 0, then it will be equal to x. If x is less than 0, this will give you minus x. This is how the modulus function works, right? Now is it 1-to-1? So getting back to our usual drill, if f of x1 is equal to f of x2, which means if mod x1 is equal to mod x2, does that imply x1 equals x2? Does that imply? No, because for a minus 1, I get a 1. For a mod of 1 also I get a 1. So even though even though I know that mod of minus 1 is equal to mod of 1, this does not imply minus 1 is equal to 1. Correct? So x1 is not equal to x2 even though I get the same y values. So this means x1 is not equal to x2 in this case, and this is not a one-to-one function. Because multiple values of y which can be equal will not have the same value of x, it will be different values of x. So every value of every element in the domain does not have a unique element in the codomain. Multiple values of elements, multiple elements in the domain map to the same element in the codomain. That's the idea of not being one-to-one. Now is it on-to? Right. For every y that belongs to R, can you find an x that belongs to R such that y is equal to mod x? For every y, can you find? No, of course not, because mod x always returns a positive value, right? So if it is greater than 0, it returns the same value or equal to 0. If it is less than 0, it returns the negative of that. So if it is a -1, it will return a 1, right? So for every negative value of y, because y has all real numbers, it also has all the negative numbers, right? So you cannot find an x, you cannot find a value. Let's say if the y value is -2, if the y value is -2, you cannot find a value of x. If you cannot find a value of x which satisfies this, you cannot get a negative value from a modulus function. Right, so this is not an onto function as well. Let's go to the next question. Okay, so we need to show that the signum function f from real numbers to real numbers is given by f of x is 1 if x is greater than 0, it's 0 if x is less than 0, and 1 if x is less than 0. Is neither one-to-one nor onto. Right, so this is the function we have. It's called the signum function. Right, so signum function is defined on real numbers to real numbers, and the function says if x is 1, it becomes 1 if x is greater than 0. Any value greater than 0, it becomes 1. Any value equal to 0, it becomes 0. And any value less than 1, it always again gives you 1. If x is less than 0, also gives you 1. Greater than 0 also gives you 1. And if it is 0, it gives you a 0. That's the signum function. Now is it one-to-one? Obviously not. It's very easy to prove this, but anyway, we know that it is neither. But anyway, let's go and do our drill. One-to-one and onto. Right, our drill is if f of x1 is f of x2. Does that mean x1 equals x2, which is signum of x? We can't really write that, but anyway. If f of x1 is f of x2, does that mean x1 equals x2? Does it imply? Obviously not, right? So for every value of x that is more than 0, it's giving you the same value. In fact, even for less than 1. In fact, for less than 0 as well. So whatever the value here is, it's either 1 or 0. But almost infinitely many values of x can be here, and infinitely many values of x can be here. So they need not be just one value. You will not get x1 equals x2. It will be, in fact, because x1 could be anything apart from 0 if it is 1, right? So it is obviously not one-to-one. Remember, one-to-one means every element here needs to be mapped only to one element here. Every element here needs to be mapped only to one element here. So signum function looks something like this, right? If you try to draw it out, you will have, this is 1 and 0, only basically two elements in the codomain, and 0 is here, and this is mapped to this, and literally every other element you can think of, every other real number is mapped to only one single element, and that is the signum function. It is clearly not one-to-one. And is it onto? So for every y, can you find, for every y that belongs to R, can you find an x that belongs to R such that f of x is y? Obviously you can't. So for every value of y in R, basically you have only two values of y in R. Every other value of y has nothing, you cannot get those values of y, right? So whatever x you input, you're only going to get 0 and 1. So literally everything else apart from 0 and 1 in y do not have an existence, and that's why it cannot be onto. So if you had rewritten this as something like, if the domain was something like f is R is mapped to the set of 0, 1, then this would be an onto function, but still only one-to-one, because every single element is mapped only to two elements. right? So this is how you can convert some functions to one-to-one and onto, but anyway, in this case, it is not onto or one-to-one. Let's go to the next question. Awesome. Let's look at the next question. Let A is a set with elements 1, 2, and 3, and B is a set with elements 4, 5, 6, and 7, and let a function f is equal to 1, 4, 2, 5, 3, 6 be a function from A to B. Show that f is 1 to 1. Okay, that's interesting. So this is where you really get to the fundamentals of what a set is, right? So a function f is defined from set A to set B, and the set A is, so the set A is 1, 2, 3, right? So set A is 1, 2, 3, and set B is 4, 5, 6, 7. Awesome. And the function we are told is 1, 4, 2, 5, and 3, 6. So we need to prove that this is 1 to 1. So what do we do? Let's go back to our usual drill, right? For 1 to 1 function proof, what do we do? If we have f of x1, so we need to prove that f of x, if f of x1 is equal to f of x2, then we need to prove f x1 equals x2. So how do we do that? So let's take any x value, right? So f of x1. So x1 is basically any value in the set A. So these are all x's. These are all x's. These are all y's, right? So any value in set A. So let's take f of 1. F of 1 is a, can you find two values of x? Or basically we need to find two values of y which are equal, right? So there is a 4, there's a 5, and there's a 6. If you have to find two values of y which are equal, so let's say there is a 4 is equal to 4. Let's take two values which are equal, 4 and 4. So if f of x1 is 4, then what would be x? There's only one possibility, right? There's only if x is 1, you could have the y to be 4, f of x1 to be 4. So f of x1 is 4 and f of x2 is 4. Then this implies x1 is equal to x2 is equal to 1. So the idea here is that if you know that the values of y are the same, so if you know that there are two values of y which are 4, you should be able to prove that there's only one way you can achieve that with the function, right? So there's only 1, 4 is the only version. If there was another function where you say, if there was another function where you said 1, 4, and there's also a possibility of 1, 5, then this function will not be 1 to 1. But in this case, whether the f of x1 is 5 or 4 or 6, you have only one way to achieve that value. So in this case, this is also a 1 to 1 function. Let's go to the next question. Right, the question number 7 says, in each of the following cases, state whether the function is 1 to 1, onto, or bijective. Justify your answer. Awesome. So let's take the first one. So the first one says, there's a function defined from real numbers to real numbers, and it's defined by f of x is equal to 3 minus 4x. So our usual drill, we need to say whether it's 1 to 1 and onto, right? So if you don't remember what bijective is any function which is both 1 to 1 as well as onto. So 1 to 1, if it is both 1 to 1 and onto, then it is bijective, right? So first we will check for 1 to 1. So what do we do for that? We will have to check if f of x1 is equal to f of x2, then is x1 equal to x2. So what is f of x1? F of x1 is 3 minus 4x. So that is 3 minus 4x1. This will be equal to 3 minus 4x2. So you cancel out the 3's and you cancel out the minus. So and you cancel out the 4 as well. So you get x1 equals x2. So that works, right? So this is a 1 to 1 function. It works. Now is it onto? You need to be able to see that for every y that belongs to R, can you find an x that belongs to R such that for every y that belongs to R, can you find an x that belongs to R such that y equals 3 minus 4x? So can you find an x for every y? Of course, right? Because we have the entire set of real numbers. For every real number that you put in here, you will get a unique value of y. For every real number of x that you put in here, you will get a unique value of y. So you will be able to find an x for every y. and that makes this an onto function. So since it is both one-to-one as well as onto, this is also a bijective function. This makes it a bijective function. So as we discussed earlier, one-to-one is also known as injective. One-to-one is also known as injective, and onto is also known as surjective. Right, so this makes it a bijective function. Awesome. Let's go to the next one. Great. So in the second one, we have a function which goes from real numbers, function defined on a set of real numbers to real numbers, defined by f of x equals 1 plus x square, right? So again, the usual drill, is it one-to-one? Is it onto? Or is it both? Let's check. One-to-one and onto. Now for it to be one-to-one, we need to prove again that f of x1 equals f of x2. Is x1 equals x2? We'll check. So this will be 1 plus x1 square is equal to 1 plus x2 square. So if you cut this out and if you take a square root on both sides, you will get x1 equals x2. So yes, so it is one-to-one function. It works. Is it onto? So for it to be onto, you need to prove for every y belongs to R, can you find an x belongs to R such that y equals 1 plus x square? Can you find? For every y, can you find an x is the question, right? For every y, can you find an x? Obviously. So because we have entire set of real numbers with us, every real number that you input in the x side, for every y, you'll be able to find some x. So you can write x as, actually no, because if you write x, so if you rewrite this, you will be able to get x equals y minus 1 square root of y minus 1, correct? So for every y, will there be an x? No, because if y is less than 1, you will not be able to find an x for that, right? If you have a y which is minus 2, if you have y equals minus 2, then this will become root of minus 3. So that does not belong to a set of real numbers. So in this case, this does not hold. So you will not be able to find an x for every y. You will be able to find all x's will give you some y, but for every y, you will not be able to find an x. So that does not work out. So this makes it not an onto function. And so this is not bijective. This is not bijective. See you in the next question. Awesome. Let's look at the next question. Let a and b be sets. Show that the function a cross b to b cross a such that f of a comma b equals b comma a is a bijective function. So we need to show it is both one-to-one as well as onto, right? That's what is a bijective, or it's both injective as well as surjective. Now, this is a slightly trickier question because we're not been given any real set, which is like an irrational numbers or real numbers or integers. We've been given a more theoretical set, right? So now, let's first understand what this means, right? So if a set A, let's take a set A which is A1, which has elements like A1, A2, A3, and so on, right? And let's take the set B, which has the elements B1, B2, B3, and so on, right? Now A cross B, A times B is also okay, but basically A cross B is a better way to say it, is a set which has the ordered pairs in correspondence with, which is basically the ordered pairs in the positions of the sets, elements of the sets itself. So the first element of set A, the first element of set A, and the first element of set B will be together. So basically that will be A1 comma B1. That will be the first element. And then you will have the second element of set A and the second element of set B together. You'll have A2 comma B2 and so on, right? So you will keep having ordered pairs like that. And that's what the set A cross B would be. And B cross A would be what? Exactly the opposite, right? Exactly the opposite means not the entire reverse of the sets, but basically the first, in the same ordered pair, you will have the element from B first and then the element from A. So you'll basically have B1 comma A1 as the first element and B2 comma A2 as the second element, and so on. Now, keeping this in mind, let's try to solve this question. So we need to show that this function, which is defined on the set, so basically the domain of this set is A cross B, right? And the codomain is B cross A. So this is the domain of this set, and this is the codomain of the set. So this set is defined from this set. This is defined from this to this, right? That is the important thing we need to keep in mind. Now the function itself is f of a comma b equals b comma a. So what is this function doing? If you can see what the function is doing, it's basically flipping these terms, right? So it takes in two terms, a and b, and it flips them. It makes them b and a. So it just reverses the order of the terms. So basically it converts this into this. That's simply what the set is doing. Now, is it one-to-one and onto? Let's check. Is it one-to-one? And is it onto? Let's check. So for it to be one-to-one, what do we need? Our usual drill is what? We need to say f of a1 comma b1 is equal to f of a2 comma b2, right? Now, if this is true, we need to show that these two, the elements inside are also equal. So that's what we used to do earlier, right? F of x1 equals f of x2. Then we need to show that x1 equals x2. If we have two elements, if we have two values in the domain, in the codomain being equal, then it necessarily means that it's coming from the same term, the same element in the domain, right? So f1 a1 comma b1 equals f of a2 comma b2. So from the function, what do we get? So this is the function, right? So if you put that in the function, what do you get? So this flips this, right? So f of a1 comma b1 will flip this. So this will basically become b1 comma a1. That's what the function does, remember? And even this, the function will flip this, right? So f of b2 comma a2, right? Now, from the definition, so if in 11th standard we learned that if two ordered pairs are equal, then each individual element is also equal. So each individual element will also be equal. That's the definition from a set we learned from in 11th standard. So this would imply that b1 equals b2 and a1 equals a2. So this proves that these two ordered pairs are basically the same. So a1 equals a2 and b1 equals b2. So these two basically the ordered pairs are the same. So this set is one-to-one, and it's actually very clear as well. So you don't need to prove it this way. This is the general proof, but you can also check from here, right? So for every a1 comma b1, you can only have b1 comma a1 as you can only just reverse the two pairs, right? So for every pair that you have, it will simply just reverse it. And since the entire set itself has been created in such a way that it is reversed, right? So the domain itself is A cross B, and the codomain itself is B cross A. The entire codomain itself is reversed of this domain, and obviously you will have a one-to-one relationship between every single element. So every element will have only one image in the codomain. So this is obviously one-to-one. And is it onto? So yes. So the drill is. So what's our usual drill for onto? So we need to say for every. Usually we say y, but in this case we'll say for every b comma a. So for every b comma a that belongs to B cross A, which is the codomain. That's what we need to understand from this. That's why this question is a little more interesting, right? Because it's not just generic. For every B comma A that belongs to B cross A, there exists an A comma B that belongs to A cross B such that f of A comma B is equal to B comma A. So for every b comma a, we need to check if there exists an a comma b. For every b comma a, does it? Obviously it does. For every b comma a, you can bet that there will be an a comma b. For every b1 comma a, for a b1 comma a1, you'll have an a1 comma b1. For b10 comma a10, you'll have an a10 comma b10. So that's how the set has been defined. So for every image in the codomain, you will have one and only one element in the domain which will satisfy the function condition. So this is an onto function. And if it is one-to-one and onto, the function is said to be bijective. Great. So let's move to the next question. All right. So this question is talking about the function f, which is defined from a set of natural numbers to natural numbers. And f of n is n plus 1 by 2 if n is odd, and n by 2 if n is even for all n belongs to natural numbers. State whether the function is bijective, justify your answer. Right. So the function is defined from natural numbers to natural numbers, and the function of n is, it is n plus 1 by 2 if n is odd. If n is odd, and n by 2 if n is even. For all n belongs to natural numbers. So all these n's are all natural numbers, right? So for all n belongs to natural numbers. Now let's get on to our usual drill, right? Is it 1 to 1? Is it on to say if it is bijective or not, right? Now, to prove it's 1 to 1, what do? We need to say f of n1 equals f of n2. If it is true, then n1 should be equal to n2. So what is f of n1? We are not sure, right? So if, let's say, now in this case we need to take two values, two types of cases. If n1 is odd and n1 is even. So let's take n1 is, let's say both n1 and n2 are odd, because only then you can say that these two are equal, right? So you can't have them equal for two different values of n, or yeah, basically that's the weird part in this case. So now that gives you a very important clue, right? So for example, if let's say n1 is odd and let's say n2 is even, which is possible, right? I can take any values of n1 and n2 and this should satisfy the condition of 1 to 1. So if this is the case, then you will get n1 plus 1 by 2 is equal to n2 by 2. So this is going to say n1 is equal to n2 minus 1. So this function is not 1 to 1, which means that every element in the domain doesn't necessarily have only one element in the codomain. It can have multiple elements. So for example, if you take n equals 2, right? So basically this function is not 1 to 1, because you can have the same value in the codomain for multiple values of. So let's see how we can prove it's not 1 to 1 from an example perspective, right? So let's take n equals 5. Let's take n equals 5 and n equals 6. So for n equals 5, what would you get? It's n is odd. If n is odd, it's n plus 1 by 2. So 5 plus 1 by 2, right? And if n is even, you get 6 by 2. So what is the value of this? 5 plus 1 by 2 is 3, right? And 6 by 2 is 3. So for different values of n, you're able to get the same value of f. So f of n is the same for f of 5 and f of 6. And that is the fundamental condition for 1 to 1, right? For 1 to 1 means every element in the domain should have only one element in the codomain. But here what's happening? Element 5 and element 6 are both pointing to the same value, which is 3. This is not a 1 to 1 function, because you can see the arrow itself is showing you. It's not like injecting into only one answer. So this is not 1 to 1. Let's check if it is on to. Is it on to? So for every y belongs to n, there exists, y is basically f of n, but yeah, that's okay. We can also say f of n. For every y that belongs to n, there exists an n that belongs to n such that y equals f of n. So for every y that belongs to n, there should exist an n. Does it exist? But basically the function is not bijective, which is already proven because it's not 1 to 1, but we're just checking to see if we are able to justify that is it 1 to 1, is it on to or not. So for every y, does there exist an n? Can you get every value of n from this function by using these two terms? So basically you need to have every multiple of 2, right? But you will get every multiple of 2 possible. So you will get so n by 2, if n is 2, you will get 1. If n is 3, you will get 2. If n is 4, you will get 2. If n is 5, you will get 3. So you will be able to generate all possible natural numbers from this function. So there exists an n such that for every y you will be able to find an n. For example, if you want to make y, so you can create this, right? So for example, if you want to find out y, so y is equal to n plus 1 by 2 if n is odd, and y is equal to n by 2 if n is even. So this means n is equal to 2y minus 1 and n is equal to 2y. So for every y, I can figure out one n, right? So if I put y is equal to 0, I get n equals 0. So I will be able to figure out, because n, in that case it's n is even, right? So I will be able to figure out an n. If I equals 1, I can figure out an n. If I equals 2, I can figure out an n. So for every y, I can figure out one value of n which belongs to the set of natural numbers. The only exception being 0, but then even y cannot be 0, right? When y belongs to n. So for every y that belongs to n, I will be able to figure out an n that belongs to the natural numbers such that y equals f of n. So this is an onto function. This is an onto function, but it is not bijective. So because it is not one-to-one, you will be able to find multiple values of f of n for every n that you can figure out. So that's why it is not one-to-one. Let's go to the next question. All right. So this is question number 10. Here we have a equals r minus 3 and b equals r minus 1. So this is basically real numbers without the number 3 and real numbers without the number 1. Now consider the function f which goes from a to b defined by f of x equals x minus 2 by x minus 3. Is f one-to-one and onto? Justify your answer. Awesome. So we clearly have defined a and b and we have the function f of x. So the f of x function is x minus 2 by x minus 3. So we need to see if it is one-to-one and onto. Is it one-to-one and is it onto? Right. Now the usual drill. So f of x1 equals f of x2. So this means if you plug this in here, x1 minus 2 by x1 minus 3 equals x2 minus 2 by x2 minus 3. So if we solve that, we can get, so if you cross multiply, what will you get? So you will get x1, x2, I'm just directly going to multiply it. So minus 2x2 minus 3x1 plus 6 equals x1, x2 minus 2x1 minus 3x2 plus 6. Right, so 6 cancels, x1, x2 cancels, and you end up with, so if you bring x2s and x1s to each side, so 2x1 and minus 3x1, so that will be minus x1 equals minus 3x2 minus 2x2, so that will be minus x2. So this means x1 equals x2. So that works out. So this works out to be true. So this means that the function f1 is onto. This works out to be onto because we started with f of x1 and f of x2 and we proved that x1 equals x2. So if this has to be true, then this has to be true. That means every element in the domain has only one element in the codomain, which is this. Right. So now let's see onto functions. So to prove if it is onto, we need to go for the usual drill, which is we need to prove that for every y that belongs to the set r minus 1 or the set B, basically there exists an x that belongs to the set r minus 3 such that y is equal to x minus 2 by x minus 3. So now to prove this, what we'll have to do is we'll have to convert this into something which is from an x perspective, from a y perspective. Now how can you do that? So what we'll do is we will cross multiply. So we'll say xy minus 3y equals x minus 2. And you can say, if you say xy minus x equals minus 2 plus 3y. So this would mean x equals 3y minus 2 by, so if you take this common, you will get y minus 1, right? So y minus 1. So this is the way we can prove. So now in this case, can you put in any value of y and will you get one value of x? So if y equals 1, that is a problem. Everything else will work out for us. But y does belong to this domain where it's not 1, right? So apart from 1, every other value of y works. So even here, apart from 1, every other value of y will give you a value of x which belongs to the set of real numbers. So this works out. This will be correct. So you will be able to say that this is an onto function as well. So this function is both one-to-one and onto. So it is bijective. Great. Let's go to the next question. Question number 11. Question number 11 says there's a function f defined from real terms to real terms such that f of x is x power 4. So we need to find out which of these options is correct. Is it 1 to 1 and on to, many to 1 and on to, 1 to 1 but not on to, neither 1 to 1 nor on to? Great. So our usual drill, go back to finding is it 1 to 1 and on to. If it is not 1 to 1, it's obviously many to 1. So now, is it 1 to 1? So our usual drill is we need to say f of x1 equals f of x2, right? If you plug this in the function, our function, then we will say x1 power 4 is equal to x2 power 4. Now, does this mean that x1 equals x2? So basically you have x1 square times x1 square is equal to x2 square times x2 square. Now the problem with a square or a power 4 is that a negative value and a positive value will give you the same answer. For example, a negative minus 1 square or a power 4, right? So a negative minus 1 power 4 will be the same as a 1 power 4. So both values of x, different values of x will give you the same answer 1. So this means that there doesn't exist only one unique value of x such that it gives you only one unique value of y. So in this case, x1 need not be equal to x2. So in this case, this is not a one-to-one function. Right? You understood? So basically in one-to-one, we need to have every element in the domain needs to have only one image, right? But in this case, you will have elements like minus 1 and 1 and minus 2 and 2 having the same value, right? So it is not a one-to-one function. This will have 1, this will have 4, right? So this is not a one-to-one function. Is it on to? Is it on to? So for every y that belongs to R, does there exist an x that belongs to R such that x power 4, y equals x power 4. So to prove this, we need to write it in the reverse, right? So if you write x equals 4th root of y. So for every y, can you find an x in the real? For every value of y in the real term, can you find an x in the real? You can't, because for every negative value of y, you will not be able to find a value of x, because a negative 4th root, a negative minus 8, 4th root of negative minus 8 or whatever negative number does not exist in the real plane. So for example, a cube root will exist. So cube root of minus 8 is basically minus 2, because minus 2 into minus 2 into minus 2 will give you a minus 8. But you can never get a minus 8 by multiplying any 4 terms. It will always end up in a positive term, right? So this does not exist in the real term, in the real set. It exists in the imaginary set. So this, you cannot find a value of every value of y, you'll not be able to find a value of x. So this is not onto as well. So this is neither 1 to 1 nor onto. Let's go to the last question. Okay. Great. Let's look at question number 12. So question number 12 talks about a function defined from a real set to a real set as f of x equals 3x. And we need to choose the correct answer. Good. Awesome. So f of x is 3x. So, and if you go for usual drill, we need to say whether it's 1 to 1 or on to, right? So how do we do that? So if it is 1 to 1, we need to prove f of x1. If f of x1 is equal to f of x2, then what do we get? We get 3x1 equals 3x2, which means x1 equals x2. Pretty straightforward, right? So it is obviously 1 to 1. That's true. Now is it on to? So for every y, does there exist an x belongs to R? For every y belongs to R. For every y belongs to R, does there exist an x which belongs to R such that y equals 3x, which means x equals y by 3, right? So for every y, you will be able to find a corresponding x, because every real value of y will satisfy this condition and you will correspondingly get the value of x. So this is onto as well. So this is both 1 to 1 as well as onto. Awesome. I hope this was helpful. I'll see you in the next video.